Hello everyone, welcome to the second lecture of this week. In the last class, we introduced the moment distribution method, and now what we will be doing today and the subsequent classes, we will demonstrate moment distribution method, the steps involved in moment distribution method through some example. Okay, so now what we do, let's take this example. It is a similar example that we use to demonstrate the steps. The only difference is now in this case these joints, it was fixed joint if you remember in the last class, and now it is not fixed, it is hinge support at C. Now the first step is to find out what are the absolute stiffnesses, and then distribution factor and carried over factor. Okay. Now let us see what is the stiffnesses for this member. Now if you remember, stiffness for this member is an idealization of this. This member is an idealization of this moment, and this member is an idealization of this. It is hinge support and a moment is applied here, and for this we know the stiffness is 4 EI by L, 4 EI by L, and for this we know the stiffness is 3 EI by L, 3 EI by L. Okay. Now for joint B. So then what is KBC? KBC become KBA. Okay, let us remove this first. Then what is KBA? KBA is equal to 4 EI. EI is constant in both the cases, so let us write its EI, and that is equal to LBA, which is equal to 4 by 5. Okay, and similarly KBC is equal to 3 EI by L, it is 4 EI, and this is 3 I by and length of BC, LBC, and which is equal to 3 by 5 EI. Okay. Now once we have this stiffnesses, then the distribution factor will be DF distribution factor for BA will be this divided by this plus this, and this becomes 4 by 7, and similarly distribution factor for BC will be this stiffness divided by total this plus this, and this become 3 by 7. This is the distribution factor. Okay. Now let us find out what is the carryover factor. Carryover factor is, you see, now if you remember that we discussed, if we apply a moment here, that moment will get carried over to this. Okay. But if we apply a moment at the fixed end, that moment will not carry over to other end. Okay, because that you can do the analysis and check if you apply at the fixed end, or then this will not carry over. So in this case, what happens? Carryover factor will be CBA is equal to half, and then CBC is equal to half, and CB is equal to half. So carryover factors will be half. Okay. Now okay. Now you may ask that this end is C. So if we apply a moment here, then this moment will not carried over to C. That is absolutely fine. But what happens is we do the analysis on the primary structure, right? And the primary structure, we assume these joints are fixed joints. So if we apply, when we actually carried over to the we do the iteration, we assume initially we we assume that primary structure are fixed, all the joints are fixed, therefore there will be a fixed end moments. Now once there is a fixed end moments, but because this is a hinge support, there should not be any moment, that moment need to be balanced, and in order to balance that, these carryover factors will be required. This will be clear when we actually do this iteration. So these are the information that we have right now. Okay. Now let us start it. So what information we have? This is the problem. So this is a fixed end, this is hinge, and this is hinge, and then we have an externally applied load, and then load like this. Okay. Now this is 3 kilonewton per meter, and this is 10 kilonewton, this is 5 meter, this is 2 meter and 3 meter. Okay. And then we have K, or we have distribution factor DFBA is equal to 4 by 7, and DFAB BC is equal to 3 by 7. Just now we have seen this is the distribution factor we have. So if we apply a moment at B, that moment will get distributed in A, B, C, in AB, BC, AB and BC as per this factor. Okay. Now, and then also we have carryover factor as CBA is equal to CBC is equal to CB is equal to half. Okay. This information we have. This is the information that we have. Okay. Now let us do the step. The first step is and let us find the fixed end moment. Is step 1 is fixed end moment. Okay. Step 1, let us write it here. Let us divide it in a 2 part. Okay. Now step 1 was fixed end moment. Okay. Now what is the fixed end moment? Fixed end moment will be M for AB fixed end moment, that is equal to W L square by 12, which is minus 3 into 5 square by 12, that is equal to minus 62.5 kilonewton meter. Okay. And then we have MBA F, this will be same value, but 62.5 kilonewton meter. This will be anti-clockwise, this is clockwise. Okay. Now similarly we can calculate MBC, fixed end moment for MBC is equal to minus 7.2 kilonewton meter, and MCB fixed end moment is equal to 4.8 kilonewton meter. These are the same example, similar example, same length and same load. These are the fixed end moments, and how to get the values, you can go back to the previous class and then see these values, verify these values. Okay. Now, so we have the fixed end moments, right? Let us now start the process, start the step. Now the steps are, first we take we'll do the steps in a tabular form. Now first suppose this is end A, this is end A, and let's take this is end B, but when B belongs to AB, and again this is also end B, B belongs to BC, and this is end C. Okay. Now first is we write the and then we know the carryover factors. Carryover factors for BC is 3 by 7, we have seen it, and carryover factor for BA is 4 by 7. 4 by 7. Okay. Now then and the carryover. Okay. Now, this is the distribution factor, okay, and carryover factor for all these cases is 1. For this to this and this to this, they all are half. Okay. Now, first we write the fixed end moment. What is the fixed end moment? Fixed end moment at A, this is minus 62.5. Now, when we again write the values, give the sign whether based on whether they are clockwise or anti-clockwise, and 6.25. This is 6.25, not 62.5. Please correct it. This is 6.25. 6.25. Okay. So, this is 6.25, not 62.5. Okay, 6.25, and this is 6.25. This is minus, this is plus. Okay, and then this is minus 7.2, and this is 4.8. This is 4.8. So, these are all fixed end moment, okay, which is step 1. Okay. Now, next step is we need to see what is the unbalanced moment here. What is the unbalanced moment here? You see, unbalanced moments are 0.95 in the previous example we have seen, and that unbalanced moment needs to be distributed in this and this as per this factor. Okay. So, unbalanced moment in this case is 7.2 minus 7.2 plus 6.25. So, unbalanced moment is in this case minus 0.95, okay, is equal to minus 0.95. This is the unbalanced moment. Now, we have unbalanced moment of 0.95 at joint B. Now, in order to then what is in order to balance, in order to get an equilibrium state at joint B, we need to apply 0.95 moment. This is negative moment, unbalanced moment. Then we need to apply 0.95 moment at joint B, okay, and positive 0.95. Now, this 0.95, that the balancing moment, this is the unbalanced moment. Now, the balancing moment will get distributed to BA and BC, and that how that balancing moment will get distributed in BA and BC based on their distribution factor. Okay. So, unbalanced moment is 0.95. When we write in a tabular form, you do not have to explicitly show how much is the unbalanced moment and then how much is the balancing moment. That calculation you can do separately. Now, we need to apply and 0.95 moment, 0.95 balancing moment at point B. Now, if we apply 0.95 balancing moment, what would be the distribution at B? Distribution at B will be 0.95 into 4 by 7. It is in BA. As similarly 0.95 into 3 by 7. That is in BC. And if we do that, then this value, the distributed value will be, here it is 0.54, and then this value is 0.41. So, 0.41 is essentially this value and 0.54 is essentially this value. So, this is distributed. So, this is, let us write it here explicitly, this is distributed balancing moment. So, this is distributed balancing moment, this value is. Now, once we have this, you can actually separate it in a different line, do it in a different line. Now, once we have this, now again this is also in a separate line. Okay. Now, once we have this, now this moment we have this some portion, this moment, some moment will from this will be carried over to A, and some there will be a carried over moment to C, and carryover factor we have seen all the carryover factors are half in this case. So, how much will get carried over? Half of this, and then here also how much will carry over? Half of this. So, carryover moment will be here 0.27, and in this case the carryover moment will be 0.21. It is 0.405 but 0.205, but just you can write it in a two decimal place. Okay. So, this is carryover moment, and carryover moment as shown like this, using an arrow. So, this is the carryover moment. Now, there is an interesting step here. You see, this is the fixed end, right. So, this is the moment goes to fixed end, there is no problem, but this end C, it is not it is simply supported end, right. There is a hinge support here. So, there should not be any moment, there should not be any moment here, right. Now, so equilibrium condition at B, in order to satisfy the equilibrium condition at B, we applied a clockwise moment of 0.95 here at B, and that 0.95 moment get distributed in BA and BC. Now, what is the equilibrium condition at joint C? Ideally, at joint C there should not be any moment. The fixed end moment is 4.8 is fine, but in actual structure there should not be any moment. Now, in order to satisfy the equilibrium condition at C, we need to apply a minus 0.48 balancing moment. Okay. We need to apply minus 0.48 in the balancing moment. Okay. Now, whatever moment we apply at C, the same moment will be there. So, balancing moment and distributed moment at C will be same, because there is no other members here where this balancing moment will get distributed. Whatever moment you apply at C, that will be the moment at C in CB, right. So, in this case balancing moment and distributed moment will be same. Okay. Now, once we have this, now this moment will also get carried over to this, because this idealization, if you take if you take this idealization, we consider this is a fixed end. So, this moment will also carried over to this, and how much will be the carried over moment? Carried over factor is half, and this is minus 2.4. So, this is also carried over moment. This is also carried over moment. Okay. But we do not really have to apply a balancing moment at A, because the end A is fixed end, and okay, in the actual structure also it is fixed end. So, whatever because the equilibrium needs to be set, equilibrium we are satisfying the equilibrium at C and B, and consequently whatever moment we are getting at A, that is the consequence of that. Okay. So, this is now next we need to check what is the status, what is the status of present status. Now, again you can draw a line, we can draw a line. Okay. Now, the present status is and what is this value. So, there will be no distribution from this. So, this value will be 0. Let us write the 0 value with different color. This value is 0 here. Okay. Now, what is the present status? The present status is we have an unbalanced moment of minus 2.4 at joint B, and that needs to be in order to satisfy the equilibrium condition at B, we need to apply a positive moment, positive moment at D, and that positive value of that positive moment is 2.4, and that external moment. So, this is carryover moment, right? This is carried over moment. This is carryover moment. Now, if you remember the demos in the last class, this was the complete cycle, the first part. Okay. Now what we have is this. Now, this is an unbalanced moment at B we have, and that needs to be balanced. In order to balance it, we need to apply a clockwise moment of 2.4 at B, and that moment will get transferred to BA and BC as per their distribution factor. So, we need to apply a clockwise moment of 2.4 kilonewton meter, and how much will go to BA? BA will go to 2.4 into 4 by 7 for BA, and how much will go to BC? This 2.4 into 3 by 7 goes to BC. So, this will be the distributed balancing moment. 2.4 is the total balancing moment at B, and this value is the distributed balancing moment at in BA and BC. So, what will be the distributed moment? The distributed moment will be, this becomes 1.03, and this becomes 1.37. Okay. So, this is the distributed moments, balancing distributed moment. Similarly, the balancing distributed moment at point C will be how much? This will be minus 0.21. You see, initially the fixed end moment was 4.8, we applied minus 4.8. So, point C, the equilibrium at point C is satisfied. But again, because of the moment, the balancing moment at B, we have some carried over moment of 0.21 at C, but that carried over moment again we need to balance. So, now we applied minus 0.21 balancing moment at C, and again the equilibrium will be satisfied. Okay. So, this is distributed. So, again you can draw this. So, this is distributed balancing moment, Okay. Now, once we have the distributed balancing moments, then that moment will generate some carryover moment to the other end. And how much will be the carryover moment? Now, carryover factor is 1.37. So, 1.37, half of this will go here, and this becomes 0.68, and similarly 1.03, half of will go here, and this becomes 0.52, and half of this will go here, this becomes minus 0.11. So, these are all distributed moment. These are all distributed moment. These are all carried over moment. So, these are all carried over moment. Okay. Now, once we have the carried over moment, then let us see the status. The status is, now we have unbalanced moment of minus 0.11 at joint B, and we have 0.52 unbalanced 0.52 moment at point C. Okay. Again, in order to satisfy the equilibrium at joint B, we need to apply a positive 0.11 moment at B and negative 0.52 moment at C, and this 0.11 moment at B will get distributed as per their distribution factor. So, again 0.11 0.11 the balancing moment we need to apply at B, and out of this 0.11 into 4 by 7 will go to BA, and 0.11 into 3 by 7 will go to BC. Okay. Now, what is this? How much is this value then? Then this becomes 0.05 and this becomes 0.06. So, this is carryover moment. This is carryover moment. Okay. Now, again here also we need to apply minus 0.52. Now, all these moments are again distributed balancing moment. Okay. Now, again let us see what is the present status. Present status is present status is, now again you can keep on doing this until you get balance is, now you have to define a tolerance, that how far shall we go. any iteration method, when to stop that iteration, that stopping criteria you have to give. Now, stopping criteria, one stopping criteria, when you see that the moments, that the increment in the moments that you are getting, or the change in moments you are getting, that is very small as compared to the initial fixed end moments. Okay. Now, if we stop it here, because these values are very small now, 0.06 and 0.05, these values are very small here, and again we can go on, because now this will get distributed here and this will get distributed here. We can keep on doing that. Suppose if we stop it here, then what happens? Then what is the final tally? Final tally will be, we need to add at point A, the final moment will be this plus this plus this, that will be the final moment, and this value is 5 point minus 5.29. Okay. As I said, you can continue with this, and you continue up to you get your tolerance, the tolerance that you need to specify. But suppose now if we stop it, then we will see what is the value we get. This becomes minus 5.29, and then this becomes 8.22, and this also become minus 8.22, and this become 0. Okay. Now, the reason we stopped here, because if equilibrium at B and equilibrium at C is now satisfied. Okay. So, the final moment at B is minus 5.29, moment at B is 8.22, moment at B in BC is this, and moment at C is C is equal to 0. But if you see that after adding them, that it is not the equilibrium again is not being satisfied, then again you have to continue the process. Okay. So, this is our final tally. So, this is our final tally. This is our final moment. So, this is called final. This is final moment. Okay. So, now what we have? Now, if we draw this in this structure, this is A, this is B, and this is C. At point A, the moment is minus 5.29, minus means it is anti-clockwise. So, it is anti-clockwise. This is minus 5.29, and then at point B in AB it is 8.22, means clockwise, and minus 8.22 means it is anti-clockwise. So, it is clockwise, which is 8.22, and then here it is minus 8.22, which is anti-clockwise, and then here it is 0. Here it is 0. So, these are the moments at joints. Okay. Now, and what was the actual structure? The actual structure was this. Actual structure was and actual structure something was this. Okay. And this was this is A, this is B, and this I am not writing the values of this. Now, we will be drawing the bending moment diagram. Now, bending moment diagram will be the bending moment of this plus bending moment due to this plus bending moment due to this. Okay. Now, the bending moment, if we bending moment due to this will be in this case, if we release this moment end, okay, then it becomes a simply supported, and this is also simply, so it becomes a simply supported. This is, there is a so this will be this, and for bending moment for this will be this. Okay, and this value is the total value is 9.375, and this value is 12.5. Okay. And then bending moment for this, again we have to see whether it is a hogging on sagging moment. Bending moment for this will be, it is 5.29, this is 5.29, 8.29 and this is 8.22, this is 8.22 and this point is 0. So, this you join them and then join them. So, this value is 5.29, this value is 8.22. Okay. And then what would be the bending moment? Bending moment for this? Bending moment will be, this part is the bending moment on the beam. This is one way of drawing bending moment. Another way of drawing bending moment is you draw the negative part at the bottom in the compression side, and then from that you draw the positive part, and then you get a bending moment diagram for this. Now, this is the bending moment. Again, when you write bending moment like this, as I said, you need to be careful about which one is positive. So, this is positive and this is positive, right, and this is negative and this is negative, this is negative and this is negative, this is also negative. Okay. So, this is the bending moment diagram for this, and this is the step that the entire step for moment distribution method. Okay. Now, again, as I said, the idea has been to demonstrate the steps through some example, but the steps will be clear, the calculations will be clear once you solve some more example that you have to do. There are many exercises given in the book. Please follow them, do them, and be comfortable with this method. Okay, the next class again will show you the steps to some more examples. Okay, we'll stop here. Thank you. See you in the next class.